Hi, my name is Adrian Cidre, and in this video I will show you how to create this map using R. In this video we have different observations of the grey wolf in the Iberian Peninsula, and you can see these different dots, which are the different observations from the GBIF database, and they are the records between 2013 and 2024. And you can see that in the background I have this digital elevation model which shows the elevation of the terrain with some 3D effect. And you can see these areas, which are the areas with the highest density of wolves. So you can see that here we have a big density of wolves. Here we have the biggest density, and we can see that there is also some big density here, and also in this area right here. So we will see now how to create this map using R. Alright guys, so we will start creating this map. And you can find this script if you want to follow along in the comments of this video. And in the case that you only want to watch, I will try to explain everything the best I can. So I will start loading the packages. We will use the geodata package to access the GBIF database and also to download the digital elevation model. We'll need the GGNew scale for creating the visualization. We will see that at the end of the video. I will use the Gisco R to download the boundaries of the Iberian Peninsula, the Ray Shader package to create the 3D effect of our map, the SF package which is used for vectorial data, the Terra package for manipulating the raster data. I will use the Tidy Terra for accessing a color palette, and finally the Tidyverse. So now that everything is loaded, we will go to the first section, which is loading the data. And the first piece of data that we need is the study area, which is the Iberian Peninsula. And to download the Iberian Peninsula, we need to download first Portugal and then Spain. So with this function, if I execute only this part of the code, you see that we have a simple feature collection, which is one multi-polygon. And I will cast it to a polygon, so I will execute this part of the code. And you will see that instead of having one feature, we have more than one feature. And if I visualize this, you can see that we have for each of the different lands of Portugal, so we have here the different islands and the mainland, we have a different polygon, but by default we had a multi-polygon for all of them. So now that we have different polygons, we can calculate the area with this function. So if I execute this, we add this new column. And what I can do is to slice the maximum area of those polygons. So with this function, I'm just filtering out the one with the biggest area. So I will only filter out this polygon. So I will execute this and I will visualize it again. And you can see that now we don't have the islands because we only want the part of the Iberian Peninsula. And now we will do exactly the same for Spain. So if I execute this part of the code and I visualize it, you can see that we also have here the Canary Islands and also these other islands, the Balear Islands, and also this Melilla, Ceuta and Melilla. So what we need to do is again to create this area column and slice only the one with the maximum area. So I will execute this and plot it again, and we have only the part of the Iberian Peninsula. The next step is to combine these two polygons into one polygon that form the Iberian Peninsula. We can do that with the stunion function, where we add these two vectorial objects, and we can transform it to a different coordinate reference system, which is a projected one. So I will execute this and I will visualize it, and we can see that now we have the Iberian Peninsula. So the next step is to get the data of the wolf, the observations, and I want them for the last decade, which is from 2014 to 2023. So here I'm mapping a function to this vector where I have the code for Spain and the code for Portugal. And the function that I will use is this one, sp occurrence from the geodata package. And here I need to introduce the Latin name of the wolf, which is Canis lupus. And here in these arguments, I can add some extra arguments for the API of GBIF. And here for the year, we need to specify first the first year and separate it by a comma the second year. And with this, we are taking all the data from 2014 to 2023. And here I'm specifying the country with these two ISO code. And since I'm mapping the function, first we will paste this S here, and then we will paste the PT. So we will execute this function twice, and we will get a list. So I will execute it, and we see that 859 records were found, and these are for Spain because it's run first, and then we find 591 for Portugal. And now if I print this in the console, and if I scroll up, we have many columns. Here we have one element of the list. So from here until the end, we have all the data for Portugal. And if I go up, we can see here this number one, saying that this is the first element of the list. So this is the data for Spain. So now the next step is to get the digital elevation model, and I will use this elevation global function from the geodata package. I take the highest resolution and I store it in the temporary directory. And then what I do here is to crop it to the Iberia polygon. But first I will execute this part of the code, and you will see that the first time it needs to download this file. So it will take a while, so I will stop the video and come back when it's finished. Okay, so now it's finished, and we can see here that we have this spot raster with these dimensions that are for all the world, and we have this coordinate reference system, which is the world geodesic system from the 84. So what I'm doing here is to crop this elevation raster by using the Iberia SF from before. But if you remember, we transformed the coordinate reference system to a projected one. So here what I'm doing is to reproject it before cropping it, so it will have the same coordinate reference system as the elevation, so we can do this crop safely. And then what I'm doing is to mask the values that are outside the bounding box. So if I execute this part of the code, you will see that now it's very fast because it's using the previously downloaded digital elevation model in the temporary directory, so it doesn't have to download it again. And now we have this other raster, which you can see that is much smaller than the previous one that had these dimensions. And we have this coordinate reference system, the world geodesic system. So what I'm doing here in the end is to project it to the UTM coordinates. So I will execute it, and I will print it again. And now we have it with this ETRS89 UTM sum 30N, which is this code, this CPCG code. So the next step is to prepare the data, and we will start preparing the wolf data. And if you remember, we have a list with two different elements. So with this lister bind, what I'm doing is to bind the list into just one data frame. So since both of the data frames that are inside the list, they have the same columns, it's easy to make this bind. So now we have only one element, and we can convert it to an SF object. And if I only execute this part of the code and I use the glimpse function, you can see that we have all of these columns, which are 135. We can find two columns, which are the longitude and the latitude. So what I'm doing here is to convert this data frame to an SF object by using the coordinate columns and saying that these coordinates are in this coordinate reference system, which is the one that we saw before, the world geodesic system 84. So if I execute this part of the code, what we have is one simple feature object that we can see here, where we have the geometry of points. And the next step here is to transform it to the same coordinate reference system as before. And one thing to note here is that, well, actually I will run just this part of the code, and I will visualize it. So I will execute it, and you can see that we have some observations that are outside of the Iberian Peninsula. So with the st intersection function, we will remove those observations that are outside the boundaries of Iberia. So I will execute this part of the code, and you will see that now we only have the ones that are inside this polygon. And what I'm doing here is to select only the country column because I don't need the other 135 columns. So I will execute this, visualize it again to check that it's still the same, and we can go to the next step. One thing that we will do here is to plot these different observations by using geom_point and not geom_sf. And this is because geom_sf may give us some problems when we use ray shader, so I prefer to use the geom_point. So here I'm taking this SF object, which is this one right here, and by using the mutate function, I'm extracting the coordinates, which if I use this part of the code, you will see that this is a matrix where we have, well, actually I will go faster like this, where we have the x coordinate and the y coordinate. So here I'm taking the first column and then the second column. So if I execute this part of the code, you will see that now we added the coordinates that come from this geometry column. So we have them in two different columns. And then I'm converting it to a table, so it will be easier to generate a new plot by using the geom_point function. So I will execute this again, and now we will prepare the digital elevation model. And in the same way, the ray shader package will give us some problems if we try to plot the raster by using the tidyterra package. So the best way is to transform it also to a table. So here I'm using this argument xy equal to true. So if I execute this part of the code, we get a table with the different coordinates of the raster and the values of the elevation in each of the pixels. So then I will remove the NA values, which are the ones that are in the bounding box but outside the polygon. So I use the NA omit, and then I rename this column to be called elevation. So if I execute this part of the code and I print it again in the console, now we have this last table with almost 1 million rows. So now we go to the last part of the code, which is creating the visualization. And here I'm starting with the wolf table, which is this one right here. And first I'm adding a geom raster where I add this digital elevation model, and I specify three aesthetics: the x coordinate, the y coordinate, and the elevation. And this looks like this, but in the next piece of code, what I'm doing is to change the style of this field aesthetic. So if I execute this part of the code, what I'm doing is to use this color palette that comes from the tidyterra package, and I'm using this guide. So this guide is related to this legend, so I'm renaming it. I'm adjusting the title to the center. I'm saying the position that I want it inside the plot, and then I'm specifying some dimensions for this bar. But then here I have this argument here, this legend position inside, which is used to specify the coordinates where I want this legend to be. So I am specifying 85% of the x-axis, so approximately here, and 30% of the y-axis, so approximately here. So the legend will be moved in the end to this part here. But we will start seeing the rest part of the code, and here you see that I added this function new scale field, and this comes from the GG new scale package. And I need to use this because then I will use another scale field. And so since I want to modify two field aesthetics, I need to create a new one because otherwise it will get messy. So now I will start executing only this part of the code. Here I'm adding this stat density 2D, and the data that I'm using is the wolf table because I didn't specify other different data. And you can see that I specify the x coordinate, the y coordinate, And then the fill aesthetic, I use this after stat level. And this is something that you need to use in the case that you want this to look in this way. So we have this kernel density. And then we choose the geometry of the density to be a polygon. I use an alpha of 0.1, so it's almost transparent. I use this argument to create the beams of this density, and I say that I don't want to show the legend of this geometry. Then I add the points of the wolf dataset. So if I execute this part of the code, we will just add the geometry of the points above this density layer. I will make this a little bit bigger so we can see it better. And there we have the different points. And then I'm using this scale fill gradient n. And if I execute until there, what I'm doing is just to add a new color palette for the density layer. And now it looks like this. But if I didn't specify this new scale fill, I will comment it out. You will see what would be the result. So if I execute this part without this new scale fill, you see that here scale for fill is already present. Adding another scale for fill will replace the existing scale. And you can see that now what is happening is that this one is ignored and it's using this one for this layer and also for this one. So we don't want that, so I will add this new scale fill again. So this fill scale will be for this layer here, and this other fill will be for this other layer. Then what I added here are some labels. Where are wolves seen the most in the Iberian Peninsula? I added the caption and I changed some theme options. So now I will execute everything and I will print the final map. And one thing that you can note is that I added the color of the text to be snow, so this will be white and we won't see anything, but we will change this in a moment. And now you can see that the map starts to look better. So the next and final step is to create the 3D map. And to do so, first I will extract the dimensions of the digital elevation model so we can create a 3D map that maintain the same difference of scale. So if I print this H and I print this W, you see that the H is a bit smaller than the W, so the height is smaller than the width of the digital elevation model. And then I use this plot.gg where I introduce the map that we created before. I specify here some dimensions that I believe they are in inches, so that's why I have to divide them, because this in inches would be very high. Then this is the scale of the spike, so for the 3D effect, and I say that I don't want it to be solid. The zoom is how much do we want to zoom in the map, and this parameter you need to experiment with it to get the correct one. And here I'm giving it a little bit of angle to upwards, and that's pretty much all. So I will execute this and it will take a couple of minutes and it will show us an RGL window. After 1 minute or so, you will see this window, and here you can move it a little bit if you want, but this is more or less how it will look when you export it. And you can see here that now the zoom is good, but in the case that you wanted to experiment with other different dimensions, you can use this render camera, which is faster, and here you can experiment with these three arguments, the theta, phi, and zoom. So here I can specify a different zoom, for instance 0.6, and if I execute it and come back to the window, you will see how it changes. So I will make this a little bit smaller here. And here if I change to 0.7 for instance, you will see how it changes. And with this phi angle, what I'm doing, if I put it smaller, let's say 60, you see how it changes. So I will say now 40, and you will see that it's rotating in different directions. So if I say 10 for instance, now we have this. So if I go back to 85, I don't know why it's like this, it should be turned around. So here I will put the same dimensions that I had before. And yeah, sometimes this get a little bit buggy, so what I need to do is to run again this plot.gg and wait a minute for it to be okay again. And after this is done, what I'm doing is to use this render high quality, which is used to export already the previous plot, but in higher quality. So here I need to specify the width and the height. So I will maintain the same dimensions that the digital elevation model has. And here I say that I want to preview it while it's rendering, that I want some light, and I will use the environment light from this file that I downloaded from the internet. You can find different HDR files, and these HDR files are used to create some environment for the background of your plot. And I said that the intensity of this environment light should be 1, and I don't want it to be interactive. So I will execute it, and the final map will take maybe 5 to 10 minutes to render. And here we have the final result. So you can see that it looks very nice. We have this 3D effect for the different mountains, and I think it looks very good. And you can see that the area with the highest density of wolves is here in the northwest area of the Iberian Peninsula, but in this area also we have many observations. We have also many observations we can see here in Catalonia, but we see that the kernel density is not so high as in the other areas that we can see in the map.